Welcome, Calculus AB. This is lesson 1-4, Limits and Continuity. Let's begin. So this is a new concept for you guys. This is the idea of limits. I want you to look at that picture, the GIF or GIF. See this dot right here represents a point on this graph, and it's moving along, and then it stops right here. So there's an idea that, like, if I look at the y values, what's the y value that it's approaching? It's hitting up here, so it's going to 1. So if you follow this path, and you follow the path of the line, the dot that follows the function, when it gets to x equals 2, I see that the y value is going to be 1. This is the idea of a limit. It's the y value that I expect to get. So if it follows this path all the way into x equals 2, I expect that when it hits here, it's going to hit 1. All right? I mean, I know I can look at that line, but if I have a dot that follows this graph, it's following the function. When it hits the point where x equals 2, I expect it to hit y equals 1. All right, just be amazed. Now, let's look at another graph, and this is not animated. So I'm going to have this point, and it's following along here. But there's something different right here. When it gets to x equals 3, there's a hole. What? So what's going on with the limit value right here is if I have a point, it can follow along this line. And as long as it's following the path of this, when it gets to 3, I'm kind of expecting the y value to be 0. But what actually happens is there's an open hole right here. So at x equals 3, or x equals 3, y does not exist. But wait, I expected if it follows this path, it would be 0. And this is where limits come in. Limits are the idea that when you follow the path, as you get close to a number, or even if I came from this direction too, I can come from the right direction or the left direction, I expect that this is going to correspond to 0. But it's not 0 sometimes. Sometimes in that last graph, it was that number. It is that number. But sometimes, maybe the graph has an open hole right there, or it doesn't exist at that point, and it's actually not 0. But the limit is what it looks like as it's going towards that point. If I followed the path, everything around that point, it looks like it's 0, but when you actually get there, it does not exist. And this is where the idea of limits comes in. Sometimes you want to know like what the graph looks like it's going towards, but when you actually get to a point, something weird happens. But you can say, well, I know there's something about that. I know it's going to 0, but the point there doesn't exist. It's kind of weird. New concept here. Another way to explain this. What you want to know is limits are y values. When I say find the limit, I want you to find the y value. Usually you're giving an x value. So if I said, what is the limit when x equals 1? Well, what's the y value the graph is approaching? It's not just the right side, it's the left side. It looks like the y value is 1. If I said when x equals 2, and if you followed the graph, well, when x equals 2, it's all the way up here, and you're approaching y equals 4. So that's the limit when x equals 2. So sometimes it's just, hey, plug it on the graph, but as you saw in that last example, if there's a hole, you can't just plug it in. Here's another example. So this is the equation x cubed minus 1 over x minus 1. Notice it looks like this parabola, but we got a hole right here, and this hole happens when x equals 1. So I'm going to ask you, let's do this first. If I said find f of 0, so this is find what the y value is when x equals 0. And that happens, x equals 0 happens right on the y-axis. That is going to be 1. And if you look at the graph, what is f of x getting close to as x approaches 0? Well, it's also getting close to 1. So f of 0 is 1, and as you're approaching it, it is 1 as well. However, what if I said, what is f of 1? This is where that open hole is. F of 1, there's nothing here. It's an open hole. We say it does not exist. What is f of x getting close to as x approaches 1? We can see from both sides, and it has to be both directions. It looks like it's approaching 3. So the limit is 3, but when you plug it in, it's actually 0. So, and here's the limit notation. You want to write this down. Again, limits are y values. So, and this is going to that. We have this limit as x approaches 1 of the some function equals 3. So I say that the limit of f of x as x approaches 1, this is x approaches 1, is 3 or equals 3. This is the format of a limit. So this is kind of like the general form. So right here, we sometimes say equals L. This is your y value. And this is your x value. And this is just whatever function. So this is our limit notation. All right. Now, a few other rules for limits right now. The limit must be the same from the left and right side. So, or it does not exist. So for example, if the left and right had to both go to 3 for the limit to be 3 in this case. If they go to different things, we say it does not exist. Limits, again, are y values. I'll keep saying that. And one-sided limits exist. So you'll see some examples where maybe I only look at the limit on the left side or look at the limit on the right side, and they might approach different numbers. So this is just to get more information from a graph when maybe you're not able to plug in a point. And this is a really good example. So again, limit is a y value. I'm actually going to go through all this. We're going to evaluate this from this function here. There's a lot of different things going on. I have some holes. We call this like the hole right here, but then there's the point's actually down here. And this is a hole like you saw before. This is an asymptote. We call this a jump right here. So this is called a jump. So it goes, and this is where piecewise functions come in. So if I said the limit as x approaches -4, so x is -4 is here. So it can left and right. What's the y value? Well, it looks like it's approaching 1. And if I plugged in f of -4, that means you're actually plugging in -4 for x. That's the dot right here. It is also 1, the y value. Now, limit as x approaches -1. So -1's right here. It looks like I'm approaching 4 from the left and right. So we can say 4. However, f of -1, when you plug in the y value, it is not 4. It's this point, which is 1. Let's approach is approaching 2. If you're approaching 2, you're approaching 1. But if you plug in f of 2, there is no dot, and there's no other dot in this line. We say it does not exist. Now let's try limit as x approaching 3. 3 is this asymptote. It's going down forever. So one thing with limits is they actually have to be a number. So when it's not a number, we can say it does not exist. We can also say, hey, since the left and right are going to -infinity, side note, we can also say -infinity. That's okay too. Now f of 3, there is no 3, so we say it does not exist. Limit of 5. So 5, now this is where left and right are different. As you go to the left, it's going to right here. It's going to -1. But if you're going from the right, it's going to 2. These are different numbers, so we say it does not exist. Now, if you plug in f of 5, where is the dot filled in? It's filled in right here. We can say it's 2 because this has the filled in dot. There'll always only be one filled in dot for a function, or it won't pass the vertical line test. Look at that again. And so let's talk about one-sided limits. That's what we talked about before. So this is the notation for one-sided limits. When I say x approaching 5 with a minus sign, negative sign means from the left. So I'm going to say from left. So the left-hand side of 5 is going to be in red. And it's approaching -1 because that's the y value. Now, when there's a plus after the 5, this is from the right. So you're approaching from the right, moving left, and that's kind of weird, but from the right. So you can think of it as from the right or bigger than 5, and from the left would be smaller. So when you approach 5 from the right, you're approaching 2, because that's the y value. All right, continuity. So this is another concept. We talk about continuous functions, and the basic idea, the easy way to explain this is called the pencil test. If you can draw it without lifting your pencil, that means it is continuous, means it's connected everywhere. So let's take a graph and go back to this. Let's say this function. This is continuous, because I could draw that parabola without lifting up a pencil. This is not continuous, because if I try to draw it, when I get to this hole, I must lift up my pencil and jump to the other side. If I go back to this function, this whole thing is not continuous, because to draw this, I would have to lift up right here, and here, and here, and here. So it's not a continuous function. The easy way is saying the pencil test. And there's a formal definition. It can't have holes, vertical asymptotes, or jumps or breaks. Or we talk about this oscillating discontinuity. We'll get to that later in class. So look in this example. It's not, list where it's not continuous, It's not continuous at x equals -1 and 2 because these have holes. Holes are when you have holes in the graph. It's also not continuous at x equals 3, which is right here, because you have an asymptote, a vertical asymptote. It's also not continuous at 5, right here, because you have a jump. So there's 4 places right here where it's not continuous. Okay, we have this concept of removable. Removable happen when you have holes. And it basically means if you can fill it in with just a hole, it's removable. So which ones are removable? Well, that's x equals -1 and 2. Asymptotes and jumps are not removable because you can't just fill in a hole. This is an infinite hole. Can't fill that in. This hole is too big. It's only when you have like a little hole right here when you can plug it in. We'll talk more about that later. All right, an idea with finding limits, let's say if you don't have a graph, sometimes you just have to plug it in. So sometimes you just directly substitute, especially when they're continuous functions. So x equals 3. If I plug in 3 for x, I just get 3 times 3 squared plus 2, which is 27, plus 2, which is 29. Same thing over here. If I plug in 1, I get 1 squared plus 1 over 1 plus 1, which is 2 over 2, which is 1. And we can save those for later. All right, so sometimes you just directly plug in. Sometimes we have this concept of piecewise functions. So one-sided limits. These are really big for one-sided limits. Again, it's different functions on the left and right. So a good example of piecewise would be where in this past graph, this is piecewise. The left and right are different functions. They behave differently. So sometimes we talk about total. If you want to find the one-sided limit, we have to check. Sometimes we check left and right. So in this case, when I say x approaches 1, I must check the left and the right side. Since this is where I like to call them piecewise, the handoff happens. We'll do this more in class too. You have to check that the left and right approach the same graph. So what I'm going to do is I'm going to plug in 3 for both. If I plug in 3 for the top, I get 4 minus 3, which equals 1. I mean, not 3. I'm going to plug in 1. 4 minus 1, which equals 3. And if I plug in 1 for the bottom, I get 4 times 1 minus 1 squared, which is 4 minus 1, which is also 3. Since both are the same, I can say my limit is 3. And this happens when two piecewise functions, basically they're connected right there. In this one, let's try the g function as x approaches 1. Well, if you plug 1 in, I get 3 times 1 minus 1 cubed, which is going to be 3 minus 1, which is going to be 2. And if you plug in for the bottom one, you can get 2 times 1 squared minus 1, which is 2 minus 1, which is 1. These numbers are different, so we say the limit does not exist. All right, we'll do more of that later. Greatest integer function. Quickly, greatest integer less than or equal to x. Sometimes this pops up. Think of it as like double absolute value lines. You'll form these graphs like this. Sometimes we call these step graphs. So here's the concept of this. If I say the greatest integer of 2.1, and we say greatest integer less than that number, the greatest integer less than number would be 2, because that's biggest integer less than 2.1. If I said 1.9 greatest integer, it would be 1. However, if I said the greatest integer of -1.1, this actually is -2 because you have to go down. It's not just chopping off the decimal. Okay, we'll do more of those examples in class. And that's going to be it.